In this session, we will be discussing about the stochastic processes. Basically, whenever I use the word stochastic process, it is a series of observations gathered over a period of time. Over different periods of time, I am gathering the observations. For example, I am gathering the stock price data, probably at the end of every day. So the collection, the list of this stock price data collected over different periods of time, probably in short represented with xt. So it could be x1 at the end of first day, the stock price could be x2 at the end of the second, and so on. It could be xn at the end of nth day. So this entire collection x1 to xn, in short represented by xt, which could be either x1, x2, x3, so on, xn, where t is at different points in time, which is again t belongs to some time set called j. So whenever we are defining a stochastic process, we are simply talking about some process xt, means different values of a particular process like stock price, or probably a state of health of a particular firm, or health of a particular person, individual. So anything, any observation which we are collecting over different points in time is what we are calling as a stochastic process. So this can be represented as xt, where t belongs to a time period j. So this xt, which are the different observations of our random variable. We are here using the word random variable because xt can take different values on a random fashion. So this set xt is what we are calling as the state space. The different possible values which our random variable can take is what we are calling as a state space, and this t, which is the different time points at which we are observing our random variable, is called as time set or time domain, right? So that's the basic thing in stochastic process. Whenever on the contrary side, I can talk about a static process where I am observing one variable at a point in time. One variable at a point in time, at one point in time. Whereas when I am talking of stochastic, I am looking at the pattern over different points in time. Now this is where comes additional understanding with respect to the stochastic processes, whether there exists any kind of dependency on the various variables that are captured at different points in time. So is there any relationship between x1, x2, x3, so on, xn? Are they interrelated? Or there is a lot of independence between them? So it requires, the study of a stochastic process requires a clear understanding of the various individual values. It also necessitates us to understand the variances that are existing, the deviations that are existing between the values, and also some level of interrelationships that are existing, something in the form of correlations or interrelationships that are existing between the variables, between the various observations done at different points in time, right? So that is what is the basic overview of the stochastic process. And just moving further, we would like to know, as far as the stochastic processes are concerned, the first thing is the classification I do with the stochastic processes. What do I mean by the classification here? We are talking about two major elements here, the state space and the time domain. Now this is where we can talk about the state space being either continuous or discrete, and similarly the time domain also could be either continuous or discrete. What do I mean by this? When I am talking about state space being discrete, it means that the possible values that could come for my random variable could be only a few. For example, I can look at the states only as integers. In case of stock price, I talk about the state space is continuous because any price literally can come up. Now, need not be an integer, even it could be in terms of decimals. So the stock price can be more of a continuous state space, whereas when I talk about, let's say, number of defaults, it may not have 2.5 default, 3.2 default. It's a set of integers only, and that too positive integers only. It may not take negative values, and where is a discrete set of values that could be taken by the random variable. So wherever our variable can take only a few set of values, we are associating it with a discrete state space. Wherever any possible value can be taken, we are associating it with the continuous state space. Similarly, when I am talking about the time domain, when the observations are made at specific points in time, when the observation of the variable is done only at specific points in time, for example, at the end of every month, at the end of every year, or on the 15th of particular month. So whenever I am making an observations only at specific points in time of that random variable, then we are saying that the time domain is discrete. But if I see that observations can come at any point in time on a continuous basis, right? Probably let's say if I am noting, let's say I'm noting out the accidents that have occurred. I'm observing the accidents that have occurred. The moment an accident is occurred, if I make an entry for it, it's like I'm doing it on a continuous time basis. But all the accidents that have occurred during a particular month, I'm recording them at the end of the month. This is where we are calling as the time domain is discrete. So, for our understanding of the stochastic processes, we look at different processes falling into different kinds of combinations. So we can talk about a process which is discrete state space as well as discrete time, or we can talk about discrete state space but continuous time, continuous state space, discrete time, continuous state space, continuous time. We can see all possible combinations that can come out with respect to our observation, but all these four form into our category of stochastic processes. So wherever I am looking at observations over a period of time, whether it is a discrete time or continuous time, discrete space or continuous space, come into the category of stochastic processes. So if I look at this first one, discrete state, discrete time, there could be multiple real world examples there. One that comes to me, comes to my understanding is, let's say, the credit rating system, wherein we talk about moving from a particular company moving from X credit rating to Y credit rating at the end of the year. So the ratings done or the observation of the credit rating of a particular company and changing it to a new credit rating could be done only at the end of the year, and probably there could be possibly hardly 10 different ratings or 20 different ratings, right? Probably a company could be a AAA rated or AA rated or probably B rated or probably C rated, but the movement from this to this, I may be observing this movement only at the end of the year or at the end of a particular period. It may not happen on a day-to-day basis. Similarly, we can talk about the no claim discount system, which is followed by the insurance companies. They may talk about 4 or 5 different layers of discount, probably 10% discount, 20% discount, 40% discount, 50% discount, or 0% discount. Now, these are the only 5 possible states for the variable at any point in time, and this will change based on the claims made by the policyholder during a particular year. So we are observing the changes from one state to the other state only at the end of the year. So the random variable will change its value only at the end of the year and nowhere in between. So whenever we are making any such kind of observations where the time set is discrete, the state space is discrete, we are classifying those kind of stochastic processes as discrete state, discrete time kind of stochastic processes. Rather than that, if the same process occurs in a continuous time, probably here we are talking about moving from a limited set of states. Let's say we are talking about a healthy person or a sick person or death. 3 major states. So a person can move from healthy to sick at any point in time, or probably from sick to healthy again at any point in time. I don't want to, here if I want to look at only at the end of the year how many people moved from healthy to sick state, then we are calling it as a discrete time. But when I am looking at it on a continuous basis, when I am observing, okay, what is the transition from healthy state to a sick state, or probably sick to healthy, or sick to dead, or healthy to dead. So when I am trying to observe the data or observe the values taken by my random variable xt, wherein this xt could be only equal to h or it could be equal to S, or it could be equal to D. Means the different possible values for my xt are very few. That is where we are talking of discrete. And but the time domain is almost continuous. I can observe the process at any point in time. That is where I am referring to discrete state but continuous time kind of a process. And on the other side, we can very well talk about the continuous state as well as discrete time, or continuous state, continuous time kind of process. Probably here, if I am talking about the stock prices collected at the end of the day, if I am talking about the stock prices collected at the end of the day, it's like a discrete time, but I am looking at it as a continuous state, because the stock price need not be any integer or any predefined list of numbers. It could be anything rounded to two decimal points. So probably the stock prices which I am collecting at the end of the day, or probably I am talking about the claim amounts at the end of every day or every month. Total claim amounts at the end of the month, if I am taking, then it is also a continuous state space but a discrete time. But if the same claim amounts, instead of being collected at the end of the month, if I am talking of as and when the claim occurs, as and when the claim is reported, if I am trying to find out the total number of claims or total claim amount is a continuous state, because any value can come out, but claim numbers could still be a discrete space because they could be only integers, right? So whenever we are trying to model a stochastic process, our understanding is I need to first know whether it is in a continuous time space or in a discrete time space, or is it operating in a continuous state space or in a discrete state space. And different examples can be talked about for each of these different kinds of processes. And in some cases, the process which we are going to observe may fall even into a mixed type. This mixed type is more associated with a time domain. The mixed is associated with the time domain. There could be a discrete as well as continuous in the process. Right? There could be some processes where the time domain could be partly discrete and partly continuous. The state space wise, nothing to bother. It could be either discrete or continuous. I'm not bothered about the state space. But when I'm using the word mixed type, it is primarily associated with a time domain where we talk about there is a combination of a discrete and a continuous time domain that is operating there. Especially when I am talking about a process where let's say there is a process where I am trying to observe some probably a pension process where the employees are given an option, where an option exists for the employee to retire early on a birthday, Whereas so any retirement that the employee wants to do, he can do only on a birthday. Means there are only discrete time points I am observing whether the employee is using his early retirement benefit or not. Only on the birthdays I am going to observe, not on any other. Or probably the retirement on early retirement can happen only on 31st of December any year. So my observation is only on 31st December and at no other time. Whereas when I am talking of death, I want to monitor it regularly or continuously. The moment the person is dead, the benefits will be worked out accordingly. Means the observation of the death is happening at continuous period of time, whereas the observation of the retirements is happening only on, let's say, 31st December or on the birthday of the person. So which means I am observing the process, a part of the process in continuous time, a part of the process in discrete time. So these kind of processes where I would be observing both continuous time as well as discrete time, we are classifying them as mixed processes. So basically, just to quickly look at this stuff, any process which we are getting to understand or trying to model for future purposes, we have to clearly understand whether we are going to observe that particular process in continuous time or discrete time, whether we are going to have continuous states or discrete states for that particular process, or would we be depending on some kind of a mixed time wherein some part of the process would be observed on a continuous basis and something on a discrete basis. So some kind of clarity on the basic characteristic of the process which we are trying to model needs to be understood, which is when detailed properties of those kind of models we would be discussing slightly later, which will help us in choosing an appropriate model. And just as uh, just as one more additional point here, one of the important processes we will be looking at is, let's say, the counting process. Now just see whether it is continuous time or discrete time. It can be any, right? See, I want to do a counting, probably number of deaths, right? So when I'm saying xt here, xt I am modeling the number of deaths or number of defaults. I'm trying to model this particular element. Now, if xt probably x0 at 0 point in time, probably there could be 0 deaths. Probably after some point, let's say after three periods, the deaths could be 1. Let's say after 5 periods, the deaths could be 2. Now this is a process where xt keeps incrementing only. Xt keeps growing with time. The value of xt increases or grows as t increases. But it cannot fall, or rather than saying grows, xt cannot fall as t increases. It may be either growing or staying stable. Those kind of processes where the time domain may be either continuous or discrete, but the state space is only a set of integers, that too positive integers, which can only either increase or stay stable, or stay constant but cannot decrease. So that is what we classify as a counting process. So like this we have different kinds of names associated with different kinds of processes. So anything we are trying to model with respect to this counting, there are so many applications in insurance and finance and various domains where this counting process will very well be helpful. So that is where understanding the counting process as a discrete or a continuous time process, but the state space being only integers, positive integers, or the other way you can call them as natural numbers, which cannot decrease in value, either they can increase or stay flat. So that is what we would try to understand as for every process. We'll, as we move along, we'll see few more processes. We'll talk about Poisson process. We'll talk about random walk kind of processes. We'll look at different others. Other processes, we'll see whether they are operating in continuous time, continuous space, discrete time, discrete space, and see for what kind of applications we can use those kind of processes, right? But before we get in into all those details, we really need to understand some of the key properties. What is that we would like to look at in a stochastic process, or key properties in a stochastic process, or probably I would like to say the key elements or key terminology that I really need to understand whenever I talk about the stochastic process, right? So let's move on in terms of understanding the various properties that are associated with the stochastic process. So when we talk about a stochastic process, some of the terms that we need to be quite comfortable with, we'll discuss about all these things as we move along. We'll talk about the stationarity property of the process. Is it strictly stationary or at least weakly stationary? We'll talk about these things. We'll talk about the stationarity property. What do we mean by the stationarity property? And before that, we will also look at what we mean by a sample path. For a stochastic process, what do we mean by the sample path? Then we are looking at the increments as a property of the stochastic process. Are the increments being independent or non-independent? So what do we mean by the increments are independent? Then we would also touch base upon one of the important property associated with the stochastic processes regarding the testing whether the process has a Markovian property or not. We'll see what it means by having a Markovian property, and we will also discuss about something about the filtrations aspect of the stochastic process. So these are some of the things which we really need to look at. So just to start off with this sample path. See, now that we have understood that a stochastic process is something like a random variable has been observed at various points in time. Now, this particular stochastic process, I am trying to look at the interrelationship at different points in time. So which means probably I want to see, is there any kind of relationship, let's say x1, x2, x3, x4, so on up to xn, and probably another set being x2, x3, x4, so on xn plus 1, which means these are the values from period 1 to n. These are the values from period 2 to n plus 1. Is there any kind of a relationship that is existing between these two sets of values? Or probably x11, x12, so on xn plus 10. Is there any kind of a relationship between this set and this set? So this is what we call as a joint distributions. I really want to check out for joint distribution of all x in T. So probably we call it as joint distribution of xt1, xt2, so on xtn, where t1, t2 and all, they belong to the time set, time domain, which I generally represent it with j, and for all integers. So I am looking at the properties of the interrelationship, or in short the joint distribution of the various variables, the various values taken by our random variable, irrespective of whether we are operating in the time domain discrete or continuous, and the state space being either discrete or continuous. Whatever are the values, we are trying to see the joint distribution or the interrelationship between the values across different points in time. And that is what we are calling as the sample path of a stochastic process. So a quick way to define the same is nothing but it's a joint realization or a joint distribution. Whenever we use the word sample path, we are talking about a joint distribution of the random variables xt for all t. So it could be x1, x2, xn, xt1 plus 1 plus xt1 plus 2, so on xt1 plus n. So for all times in the time domain is what we are calling as a sample path. Now our intention of the sample path is, the moment we see the sample path, we are trying to examine some of the properties based on the sample path. As I have discussed earlier, I would see whether this joint realization or joint distribution follows stationarity, or what about the increments associated with this process, or what is the Markovian property associated with this process. So I am primarily looking at the different properties that are associated with this sample path, and I am trying to see whether these properties will match the real world, to a large extent, means statistically significant level. Whether these properties which we are generating through our model, through our assumption of a particular sample path, we are seeing whether they can be replicated closer to the real world. The moment we are able to bring that approximation to the real world, which means I can very well use this model or this sample path for doing various kinds of prediction. I can use this sample path for doing various kinds of prediction. So the more and more the real world properties matching with the model based properties, the more and more it goes useful for the predictions and for the prediction of those particular variables in the future. So with that as the base, let's try to explore some of the properties that are associated with with our stochastic processes. One, I am looking at stationarity. wherein I use two words. One is either it's a strictly stationary, or we are talking of weekly stationary. Okay. Now we are talking about, let's say, one joint realization x1, x2, so on, xn. The other one I am saying xk plus 1, xk plus 2. I am just showing some k. For some k, I am taking xk1, x1 to xn, xk plus 1 to xk plus n. Assume k could be 1, 2, k could be any number. Right? Even something up to some t. So k could be any number, and we are talking of x1 to xn. Now what we are saying is, for all possible values of k, if the joint distribution between these two, so probably it's as good as saying, okay, when I am looking at x1, x2, so on, xn, and when k equal to 1, x2, x3, so on, xn plus 1. When I am trying to look at the joint distribution of these two, or x1, x2, so on, xn, means the stock prices, if you look at x as the stock price for the first n days, and the stock price from second to n plus 1th day, if I am looking at the statistical properties of these, or probably first to n days, third to n plus 2 days, or probably first to n days, and 11th to n plus 10 days, whatever the combinations I am taking, for each of these sample paths, joint realization of the sample paths, if I am looking at the joint distributions of this set or this set or this set, they should be identical. What do I mean by joint distribution is identical? All the statistical properties, whether I talk about the means or variances or covariances or correlations, all of them are identical across all these various realizations. That is when I say that the process is strictly stationary. So any process where I see that the joint realizations are having the similar statistical processes or statistical properties of these processes, they do not change with time. The mean between this from x1 to xn or x2 to xn plus 1, if the mean is going to be the same, or the variance from first day to nth day is same as the third day to n plus second day, or when I am taking the covariances between the two, it is hardly mattered when I am taking it between x1 to xn or x11 to xn plus 10, the covariances depend only on the lag, means they are not dependent on the values x1, x2, so on. So in these kind of cases, we say that the property of stationarity is satisfied by our stochastic process. So basically what we are saying is, when I look at any stationarity, especially the strict stationarity, probably just to use as an example, the probability of, if I want to really measure the probability of being alive in the next 5 years, right? This is what I am trying to measure. This is what I am trying it as my process xt. Now when I look at it between the ages of, let's say, 21 to 25, the probability of being alive for the next 5 years may be much higher. But if I am looking at it as x 51 to 55, the probability of living for the next 5 years may be slightly lesser. But if I am looking at x 71 to 75, the probability of living for the next 5 years may be much lesser. Which means here the properties of x over the next the properties of this process, the mean, the variance and the covariance, they are not constant, they are varying with the time. So if I see that the statistical processes vary with the time and they are not constant over the period, then I cannot say that this process is strictly stationary. It is non-strictly stationary kind of a process. And one thing is, if I have to look at or evaluate the property of strict stationarity, it will be very difficult in real life. So that is the reason we talk about using weak stationarity as a process, and we see whether a process which we are trying to model is at least following a weakly stationarity kind of a scenario. So when I am looking at weakly stationarity, few things. I am looking at least for this processes at different points in time, are the means constant? The expected values are typically the means. Are they constant? And the covariance between these two, probably if I am looking at the covariance between these two, it is dependent only on the time difference. Covariance is dependent only on the time difference. In this case, the time difference is 30 years. So the covariance is purely a function of 30 and it is nowhere a function of x. So it is dependent only on the time lag. So especially if I am looking at a process whose means are constant and the covariance depends only on the time lag, those kind of processes we call them as weak stationary, because getting them as a constant, observing for a strict stationarity wherein I try to observe each and every joint distribution and look at the identicality of the joint distribution for all possible combinations is very difficult to observe in the real world. That's where we are resorting to this mechanism of weak stationarity. So these two things, the expected values or the means of that process are constant, and the covariance between at any 2 points in time, between any two sets of values xt and xt plus n, the covariance depends only on the lag t plus n minus t, which is n. That is where we call that kind of a process as a weakly stationary kind of a process, right? So this is one more thing we need to be comfortable with. For any process we are trying to observe, we will have to check out whether strictly stationarity or weak stationarity is associated with that particular process. So we need to test for both the means as well as covariances to see whether our process is following the weak stationary kind of a scenario. Alright. Then the next important property that we are focusing on for any stochastic process is the increment. So basically we are focusing here on the changes from time to time in the value. So xt plus k minus xt. So over a period of k periods, over a k periods time interval, what is the change in the value of the underlying random variable. Generally, we talk about xt plus 1 minus xt, which is a kind of one period increment. The increment from last period to the current period. Now we are trying to see the behavior of these increments. So instead of looking at the properties of the variable in itself, here we are looking at the properties associated with the increment. Right? So instead of observing the properties of the original variable, we will try to observe the properties of the increment. So sometimes it's like when I'm looking at the stock prices, right? When I'm looking at the stock prices, probably I may look at this as the increment, or we can look at it in a this could be an absolute form of increment, or the same I could look at it in a percentage form, which could very well be like xt plus 1 minus xt divided by xt, or in some case I could very well go with log xt plus 1 by xt. So this is more in the form of the increment. The increment itself, I am looking at it either in an absolute form, or in case of logarithmic kind of a form, but we are more seeing whether the increment follows any kind of a stationarity or not. Sometimes it may so happen that the xt as a process may not follow a stationarity kind of a property, but some kind of modification on it, like log xt plus 1 by xt could follow a stationarity kind of a property. So we are, which is nothing but log xt plus 1, probably if I am expanding it, it is nothing but log xt plus 1 minus log xt, which is nothing but the difference between the logarithms. We are not taking the increment in its original form, we are taking the logarithmic increment, and we can see that in some cases this logarithmic increment could very well go as a part of the stationarity, either strictly or weakly stationarity kind of a process. So in short, to define the increment, especially this is what we talk about the increment, and here we use the word, we check out whether the increments are typically independent or dependent. So whenever we are saying xt plus k minus xt, which is what is the increment, it is nowhere dependent on this increment. It is nowhere dependent on probably xt minus r, or probably some earlier period, or probably on some excess where s is lesser than t. So this increment does not depend in any way on the past values of the process, right? It is a completely independent kind of an increment. So the change either in the logarithmic form or in the absolute form, if that change does not depend on any other past values, we attribute that this particular process has increments which are completely independent in nature. So it could be like this process in original xt has independent increments, I can say, or probably I can say log xt also can have independent increment, but depending on what process has an independent increment, we can actually model it accordingly, right? So we'll so one more property we have to be comfortable with respect to stochastic processes is check out whether the increments are independent or not. Then The other important property that is worth knowing with respect to the stochastic processes is the Markovian property associated with these stochastic processes. Basically, it's like, okay, we are talking about xt plus 1, so on, xt plus n. Now, when I say that the next period xt plus n plus 1, if this particular value depends only on just the immediate previous value, the probably it's as good as saying if this particular value depends only on the previous value and not on even earlier previous values. It does not depend on all these things, but it depends only on the current latest available values. We are calling that particular process satisfies the Markovian property. It's as good as saying if the today's stock price, if I say that it depends only on yesterday's price and not on all the other previous days, we say that the stock prices are going to follow a Markovian kind of a property. The stock price for today depends only on the current, yesterday's, the latest stock price and not all other prices earlier. We call that particular process to satisfy the Markovian property, right? So simply whatever we are putting, the probability that xt belongs to A, given that x probably s1 is equal to x1, it's in various states earlier, xsn xsn is equal to some xn. Let's say if this is what is the given property, then probably all we are saying is the probability of xt belongs to A. It does not depend on all these things. It depends only on xsn, which is the last state. So it is dependent only on this. Then that is where we are calling that this particular process satisfies a Markovian property. So probably it's as good as saying the probability of a person becoming sick, let's say, depends only on the current state, whether he is healthy or non-healthy, but not on the previous states, whether 2 years back he was healthy or not, whether 5 years back he was healthy or not. It does not necessitate that kind of an information. Then we say that that particular process follows a Markovian property, or in short, any process which is having independent increments. Another way to understand this is any process which is having an independent increment is bound to follow a Markovian property, not the converse. Any process with independent increments will definitely have the Markovian property, because the value for the next is dependent only on the latest plus whatever is the increment, that is completely independent and it is nowhere dependent on the previous scenarios. So that is one of the prime reasons we talk about any process which is having an independent increment will satisfy the Markovian property. Now, the other thing we need to know about the stochastic processes, the other important term to understand with respect to stochastic processes is the filtration. So the filtration for me is primarily about having an information about the process up to some time period. Filtration is nothing but we having the information, let's say from x1 to xt. I have so much of information in x1. In the first month the price was something, second month the price was something, the tenth month the price was something. So having an information from x1 to xt about that particular process is what we can simply write it as ft. ft is nothing but the filtration, which is the information I have about the process up to a time period t, is what we are calling as a filtration, right? So we know a set of events. All these events we are knowing: x1, this was the value; x2, this was the value. The all the outcomes that have occurred right from x1 to xt is something we do have, and that is what we are calling as the filtration. So probably knowing this, I would like to see probably, okay, what is the probability that xp is less than or equal to some x given a filtration of up to a period s, where s is lesser than p. Now all we are saying is I am having an information about the process up to a time period s, and using that I want to find out what is the probability that this particular process at time period p will have a value less than or equal to x. If at all it is following a Markovian kind of a property, I could very well write this as xp, probability of xp less than or equal to x given xs, because the filtration about up to this point x means I just need to know not x1, x2, x3, xs. I just need only the latest information. If it has to follow a kind of Markovian property, I want only the latest information. I don't want the information. When I write it as fs, it is like I have the information from x1 to xs. But because I am talking about a Markovian property where only the latest information is required to be known, that is where I modify this and make it as xs. So this is what is the Markovian property expressed in the form of filtrations. And just to give some names regarding the Markovian related products, if I am talking about a process in discrete time, discrete space, we call those kind, and they exhibit Markovian property, we call those kind of products as Markov chains. Those kind of processes as Markov chains. Similarly, when we talk about continuous time, discrete space, we call them as Markov jump processes, and they exhibit Markovian property. We are calling them as Markov jump processes. We'll talk about these kind of processes slightly later in more detail. But the stochastic processes which can fall with respect to the discrete state spaces can very well be modeled as Markovian processes. They can get into the world of Markov jump or Markov chain kind of processes. We can model them as those kind of processes. Alright. Now, a few more stochastic processes is what we will look at. A few more stochastic processes is what we would look at. for a better understanding. So we'll try to consider few examples primarily relating to white noise. What is white noise? What are the statistical properties, or probably whether it is stationary or not. I'll look at for each of the stochastic process. I want to see whether it is stationary or not, whether the increments are independent or not, and whether it follows a Markovian property or not. This is what we want to see for different stochastic process. So we'll look at white noise, we'll look at random walk and probably general random walk. We will look at a Poisson process. Of course, as we move along, we'll talk about a few more processes, but we'll look at a Poisson process. What is that process and what are the properties associated with that particular process? And we will also look at compound Poisson process. So these four different kinds of processes is what we'll focus on. Right, we'll understand the properties of these processes, which will give us a clarity on how this how this stochastic processes can be understood for real world examples. All right. Okay, now looking at each one separately. If I have to talk about white noise, it is a kind of a stochastic process where we talk about independent and identically distributed random variables. Typically a very basic set of values, typically called as IIDs. Means basically what is this value, this term mean? All the values are completely independent. Let's say I'm talking about the stock prices. If I'm saying the daily stock prices are IIDs, then it means the price today is nowhere dependent on the price yesterday, not dependent on yesterday's price, that is independent, and identically distributed. All of them follow a similar distribution. If typically the prices follow, let's say, normal distribution, if the prices follow a normal distribution, every day the price will follow a normal distribution but independent of the yesterday's value. Those kind of values are typically considered as following a white noise kind of a process. So typically whenever I discuss about the white noise, in this case the stock prices may not be that, because the price today is more or less dependent on yesterday's price. So it may not be the price may not follow an independent identically distributed kind of a process, but probably when we are talking about the returns, that could very well follow an IID kind of a process, right? So okay, whenever I talk about the word white noise, I can be talking about the state space being either continuous or discrete, and similarly the time domain also being either continuous or discrete. So white noise can operate in any of the four possibilities of processes, but what we are typically meaning to say is each value is independent of the other and all the values will be following a particular form of a distribution. Now in that kind of a process, so typically whenever I am talking about the values x1, x2, x3, so on, xn, for over n periods, maybe discrete, maybe continuous, right? Over this period when I am looking at them, they are all independent and identically distributed. So from that standpoint, the values are independent, but increments need not be independent. Right? Increments need not be independent. And what about the stationarity here? If all of them are following a similar kind of a distribution, then obviously the stationarity is existing, because the mean, if the distribution is more or less same, the mean is going to be the same. Mean is going to be the same across, and at the same time the covariance may depend only on the lag, or the joint probability distribution might be identical for all combinations. So from that perspective, I can see that white noise is more of a stationary kind of a distribution itself, especially when we are looking at in the discrete time kind of a space. And majorly what we see is white noise becomes an input for various stochastic processes. We'll see later when I talk about the general random walk Poisson process. We see that white noise is one of the important inputs for the stochastic kind of processes. And what about Markovian? We said that if the increments are independent, then Markov property may be satisfied, is satisfied. But here the increments are not independent, but still we see that the Markovian property satisfies, because the Markovian property is majorly saying that in order to know the current value, I just need to know the last previous value and nothing other before that. But in reality, for white noise, even this is not required, because this is completely independent and identically distributed kind of a value. So even this is not required. But the typical Markovian definition is, if at all it is dependent only on the previous value but not on any other values before that. But here even this may not be sufficient. So in a trivial way, I can say that Markovian property still holds true. For a white noise, the Markovian property still holds true. May not be in a traditional way, but in a very typical kind of a manner, because the dependency even on the last occurrence, even on the immediately previous record also does not exist. Right? Now let's move on to the next, which is the general random walk. This process again includes IIDs, independent and identically distributed random variable. So here if I talk about some xn, so first let me talk about some yn or yj's like y1, y2, y3, so on yn, being IIDs, independent and identically distributed random variables. Now probably it could be like the number of customers. Probably if I am saying number of customers in any particular day, yi, let's say let it represent the number of customers on any particular day. Now what we are saying, so on any day the number of customers which I am going to get are independent and identically distributed, and on the top of that I am defining a process called xn, which is the total number of customers. On the same, if I have to define, it is the total number of customers in the last n days. So that if I am defining as sigma yi, where I am saying I is from 1 to n. This particular process is what I am calling as general random walk. These are all random, independent, identically distributed, right? So because this is independent and identically distributed, the addition xn is always like, it depends, it can be something like this, xn minus 1 plus yn, whatever are the number of customers on the nth day, I am adding to the total number of customers up to the first n minus 1 day. So from that standpoint, the xn value is dependent only on the immediately previous value, or probably from the increment perspective, I can say xn minus 1 is yn, which is an IID. So the increments are independent here, right? And because the distribution is an identical distribution, we will find that stationarity is here the summation as the n is increasing, probably the summation can typically go up drastically, right? Because as the numbers are increasing, right, probably as n is increasing, I may find xn to be much higher. Sometimes xn, the mean can go high, the variance can go higher. So probably the stationarity may not be associated with the general random walk, but because the increments are independent, we can very well say that Markovian property holds true. And the other way to look at is xn is dependent only on the previous time period value and not on the values before it. It does not depend on xn minus 2, xn minus 3, etc. So from that dimension, we can see in case of general random walk, the Markovian property still holds true. And in this general random walk itself, if I am making sure that yi can take only values of 1 or minus 1, plus 1 or minus 1, if so, it's like either an increment or a decrement. So probably yi is yi. I talk about the number of people in a city. So it can so happen that an addition of a person with a birth can create plus 1. The subtraction of a person with a death will be taking a value minus 1. So at any point the total number of people in a city xn, I can take it as summation of yi, where yi is the birth or a death. Birth can be with a plus 1, death could be with a minus 1. So, and that can happen on a random basis, or a customer acquired and a customer lost. That also can very well be modeled through this kind of a mechanism. So where yi can take only either plus 1 or minus 1 with different probability, then we are talking about this particular process as simple random walk. And even in that, if both of them have equal probability of occurrence, this is with a probability 0.5, this is also with a probability of 0.5, then we are talking of symmetric simple random walk, right? So in case of symmetric simple random walk, because of the identicality in the distribution, it can so happen that it can follow a stationarity kind of a process. But if we are talking about xn, a general random walk where yi can be any kind of a value, we are not sure about the stationarity of the process, because the mean as well as the variance as well, they may not be constant. They are going as some kind of a proportion of the number n, right? All right. So let's look at one more process. a Poisson process. When I talk about Poisson process, here we always use the word lambda, the term lambda, which is a rate parameter. And as we know, Poisson distribution, probability of x equal to lambda, we take it as e power minus lambda, probably x equal to some x with lambda as the parameter, e power minus lambda, lambda per x by x factorial. That is what a Poisson distributed random variable values will be. So here we are talking about NT being a Poisson process, wherein we are talking about one, the increments are independent. When we see an NT as a process where the increments are independent, just like your random walk, the increments are independent, but they follow a Poisson distribution. Right? So over a point in time, over a period t, we see that initially the process n0 is equal to 0. So generally to model number of customers within 5 days, within x days, when I am looking at the number of customers during a particular process, so what we are saying, just applying the same Poisson distribution formula, probability that n5, or probably it's like n5 minus n0, because n0 equal to 0. So within a 5-day period, the probability of getting at least 3 customers. So if at all I am saying that lambda is the rate per day. So if my intention is to find out within 5 days what is the probability of getting 3 customers, then the same logic is getting, the lambda is becoming e power minus lambda into 5 minus 0. So in general, if I am saying the probability of nt minus ns is equal to some n, goes as e power minus lambda into t minus s into lambda into t minus s to the power n divided by n factorial. So here also it becomes e power minus lambda into 5 minus 0 multiplied by lambda into 5 minus 0 to the power 3 divided by 3 factorial. So that kind of a process with a rate lambda, wherein nt, they are all integer values only, because we generally use Poisson distribution to model number of customers, number of deaths, number of claims, which has a few properties. The first property being at time 0, the value should be equal to 0. And at time t, we are talking of independent increment. And we are talking of the NTs being following a Poisson kind of a distribution. This is where we are bringing in the Poisson process into the picture. And one, this is, what about the increments here? The definition itself says the increments are independent. And because the increments are independent, it will satisfy the Markovian kind of a property. And here also, as n is increasing, probably my mean, as well as because in case of Poisson distribution, as n is increasing here, we see that the mean is as time is increasing, t minus s. Here as t minus s, because the mean is lambda, in this case lambda into t minus s. As t minus s is increasing, As the time which we are looking at looking into consideration is increasing, we see that the mean is increasing, the variance is increasing, and because the mean of the process is not constant, variance of the process is not constant, we cannot say that the process is stationary. So Poisson process is not stationary. The stationarity is violated in case of a Poisson process. So typically when I am trying to use this, we are interested in modeling the number of occurrences during a particular period of time. Your number of occurrences, let's say right from the beginning up to a point t. So number of claims or number of customers added to a company, all these things can very well be modeled as Poisson processes. And the same thing, if I am extending a little bit by considering that Poisson process NT, if I am extending the process wherein we am starting with the Poisson process NT at any point in time, but at the same time, if I am defining another process xt where I am summing up over all NTs, I am summing up the independent and identically distributed random variables. This is what we are calling as compound Poisson process. Means basically it's like, okay, over a period of NT, right, over a period of NT, over a period of T, we are observing that there could be NT, the process is the number of customers arriving is what we have modeled as NT, and that follows a Poisson process. So from first customer to the NT customers, if I am finding out, let's say Yj, which I model as claim amount, which is identical and independently distributed kind of a value, if I sum out over the entire NT this claim amount, that is what we are modeling as xt. So basically it is like the total claim amount of all the customers during the time period t, because each the number of customers is following the number of customers NT is following a Poisson process, and for each customer I am finding out the claim amount, which is an independent and identically distributed random variable. So the summation of all of those customers is what I am creating as the compound Poisson process. So here also, if I am talking about xt, it is nothing but xt minus 1 plus yt. The total claim amount of x the t customers, or probably by the time t, is the total claim amount by the time t minus 1, and the extra claim amount added up by the customer NT. Probably I call it as the XNT is coming out as XNT minus 1 plus YNT. The NTth customer is adding a claim amount of something, means the increments are independent, and at the same time it is following a Markov kind of a process. But again, this, the mean of this and the variance of this will vary with the number of claims that are coming up. So the mean will always be on an increasing note. The variance also could be on an increasing note. It cannot be constant for a point in time. So that's the reason we say that this is not a stationary kind of a distribution. But the increments are independent, and Markovian property definitely holds true in this case. And we would be talking of many other applications of this compound Poisson process as we move along in our various understandings in the fields of insurance and risk management. So that is what we are trying to look at as a part of this session. So we started off right with the understanding of the basic stochastic process. Well, how do we differentiate a stochastic process from a static random phenomenon? And we also talked about the state space and time domain, and what kind of processes fall into continuous and discrete state spaces and time domains kind of stuff. Then we have also looked at the mixed type and a few properties associated with a stochastic process, or terminologies associated with stochastic process, where we understood what is a sample path or a joint distribution or a joint realization of a random variables. Or we also looked at a few more terms like stationarity in terms of strictly stationary as well as weakly stationary. Then we had discussed about the increments and the independence of the increments, the Markovian property, and what do we mean by the word filtration, and how do I express Markov property in terms of filtration. Then we have discussed a few important processes. One is on the counting process, the white noise. Then we talked about the general random walk, where we discussed about simple random walk as well as symmetric simple random walk. We talked about the normal Poisson process as well as a compound Poisson process. For each of the processes, understood what do we mean by stationarity of that process, is does that process have independent increments, and finally does that follow a Markovian kind of a scenario, right? So this is what I would like to this is what I thought I should cover as a part of this session. Any further queries you have regarding this, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.